Okay, so we've got another example to do with statics in rigid bodies. So we've got a uniform rod AB, mass 6 kilograms, length 4 meters, smoothly hinged at A, and then a light inextensible string is attached to the rod at point C, where AC is 3 meters, and to a point D vertical above A. The string keeps the rod in equilibrium in a horizontal position, and the angle between the string and the rod is 40 degrees. Calculate the tension in the string and the magnitude and direction of the force exerted on the rod by the wall. So I already started drawing a diagram and then dropped the camera, which was like this. So we've got the wall here. The rod is attached at point A, the other end is B, and the rod is 4 meters long. Point C is where the string is attached, and that was 3 meters from A. The string goes up to point D vertical of A, and then start labelling forces. So the weight's the obvious one to go on, which will be in the centre of the rod because it's uniform. So it's got a mass of 6 kilograms, so the weight is 6G. There's tension in the string holding the rod up, and the other force that I need to add is going to be at the hinge here. So hinge is a bit weird because the force from the hinge is going to be kind of like up here somewhere. But part of what we actually want to work out is the direction as well as the magnitude. So what we're actually going to do is split it into two components, X and Y. So the idea is that part of the hinge is sort of pushing the rod away from the wall, part of the hinge is actually holding the rod up so it's not falling as well. So if we do it in two components, we can then work it out. Okay, so we'll start by getting the tension in the string, because that is part A. And so to do that, we're going to take moments about A, because if we do that, it means we can ignore X and Y, because they're going through A, so they can have no turning effect. So taking moments about A, there's only going to be two forces involved here. So the 6G force will be going clockwise, so I'll call that positive. The tension will be going anti-clockwise, so I'll call that negative. So the moment of the 6G force is going to be 6G times 2 meters, because that's how far it is from A. The tension is going to be negative, and to get the moment for the tension, well, it's going to be T times the distance, which is the 3 meters, times sine 40. That was one of the rules that we had to do with calculating moments. So T times 3 sine 40 equals 0. Well, then that's just an equation for T, because 6G times 2 is a number, 3 sine 40 is just a number, so all I need to do is rearrange that to find what T is. Okay, so once I do that, that gives me T equals 60.9843740 newtons, or about 61.0 newtons if around that. Okay, so what we want to do now is use that to work out what X and Y are. So there's a number of ways we might do it. We could do something with moments still, but actually the best thing to do is going to be to resolve vertically and horizontally on the rod. Okay, so I'll start by resolving vertically. So if we go back to the diagram, we've got vertical forces are going to be the Y here, we've got 6G here. We're also going to get a component from the tension, so let's just draw a little diagram here. So this component will be T sine 40, this component here is T cos 40. Okay, so if we resolve vertically, I'm going to get Y plus T sine 40, take 6G equal to 0. Or in other words, Y is equal to 6G take T sine 40. And we already worked out T a moment ago, so I can just substitute that in. Okay, so putting that into the calculator gives me that Y is equal to 19.6 newtons. And then to find out X, I'm going to resolve horizontally. So resolving horizontally, go back to the diagram again. So we've got X going this way, which will take us positive. The only other horizontal force is the T cos 40. So X take T cos 40 is going to equal 0. So in other words, X is equal to T cos 40. And again, I can calculate that. And I get X to be 46.716740 0.83 or about 46.7 newtons. And then what we actually want to do is find the magnitude of the overall force and the direction of it. So if you remember from the diagram, we had this hinge here, and we split it into two components. So rather than these being separate forces, this is just two components of one overall force. So if we just draw out what we've actually got, we've got X to be this 46.7 newtons. I'm going to use the whole value I calculated here. In fact, when I do my calculations, I'm just rounding it on the diagram. And I've also got Y going upwards, which is 19.6 newtons. So we want to find the overall magnitude, so this bit, and the direction. So what we really want to do is work out this angle, and we'll be able to describe it as an angle to the horizontal. So the overall magnitude of it, well, that's just Pythagoras. So the magnitude of the force, we're just going to be doing the square root of 46.7 squared, add 19.6 squared. Okay, and for that I get a magnitude of 50.7 newtons. Then direction, we just want to work out this angle here, theta. So that's just going to be a trigonometry question. So we can say tan theta would be 19.6 over 46.7. And if we just do inverse tan, then we'll find out what that is. Okay, so that comes to 22.8 degrees. So we'll say the force acts at an angle (22.8 degrees) above the horizontal. And that is the question answered.